Yes, I'm happy to take it away. And FYI, Canada lets you fly solo at 14 years old. So I used to come up to Sarnia and flight train a bit, like before before I was old enough in the US. So that was fun. Just yay, Canada. So okay, so that's an aside. But the talk today is going to be about this wonderful, cool new research program called Celestial Holography, and I got to meet, or at least like host, a couple of you guys last week at a conference where we had a meeting of minds. And today I want to convince you that it's an interesting program to follow. And I know that like my talk is kind of sandwiched between two other talks on a similar subject. So hopefully you guys are going to be inundated with celestial holography, fall in love with it, and then we can do cool things together. So, okay, I'm going to structure my talk today as 3 acts about this story. So the first thing I have is my plot. I want to present celestial holography as a new framework for describing scattering. And the way that this story is going to unfold is basically in 3 parts. First, we want to see why infrared physics constrains scattering, constrains the S matrix, then how these symmetries point to a 2-dimensional or codimension 2 holographic dual, and then finally what we might gain by building this dictionary. So those are the 3 parts of the talk. And the central object of study we have is going to be the scattering matrix. And for us, we want the scattering matrix to basically describe physics at a very large range of scales. So we're talking about either collider experiments or even gravitational scattering, measuring something at LIGO. So what we run into, for instance, is we basically want this S matrix to include gravity. So when you try to find a consistent theory of quantum gravity, you run into various problems. On the one hand, you can run into issues such as renormalizability if you treat it like a field theory. And then on the other hand, if you try to say I have this curved background, I do quantum field theory on top of it, you would run into other puzzles like the information paradox. So this can be a tricky subject. Now, various people have proposals for maybe how to rethink of quantum gravity as some extra like theory that maybe is stringy in the UV, or some other way of describing physics that isn't that is a little bit different from maybe the standard approaches where we're starting from a field theory and seeing like, well, what happens now? So they resolve it from the ultraviolet short distance physics, something new is happening. What is that? But surprisingly, and what the theme of this talk is going to be about, is what we can learn about a quantum theory of gravity and the quantum gravity S matrix, starting from infrared physics. So the structure is going to be such that you see these nice features coming from the infrared, and then if you're willing to promote those features as something that has to hold for the exact S matrix, that gives you a lot of power. So that's going to be the underlying theme of the talk today, is starting from the infrared and going up. We're going to see this very enriched symmetry structure. We're going to see that it points towards reorganizing scattering amplitudes. And then we're going to see that maybe with that reorganization, we can say something that may not be obvious from the infrared itself. So we've developed this new framework that will then let us look back at scattering and maybe make claims about UV physics or other things maybe we wouldn't have thought we'd see. So let's talk about our heroine. Our hero for today is going to be Emmy Noether and Noether's theorem. The first part of the talk is going to be about basically finding these like very rich symmetry structures. So more symmetries will imply more constraints is going to be the modus operandi of the first part of the talk. And then also the holographic principle. These symmetries are going to point towards a holographic dual description of scattering. And we want to see if we can basically apply it to asymptotically flat spacetimes. So vanishing cosmological constant. A theory with quantum gravity should be equivalent to some lower dimensional theory without gravity. And we're going to propose what that CFT is. So Act 1, secrets in the infrared. Great. So the setting that we have is what are going to be called asymptotically flat spacetimes. And for a nice physical picture, you have vanishing cosmological constant, and you allow some localized stress tensor sources. So we already know we're going from not just Minkowski space to something with matter where the metric is now curved a little bit. What's going to matter for us is where massless fields come from and exit within this spacetime. So hopefully, like 2 weeks ago, you saw a Penrose diagram from Minkowski space drawn down and went into a little bit of detail with that. So I am going to present what I want from it now. But so the key things to keep in mind is when I'm talking about these spacetimes, they're going to have the same boundary structure as if I just did a Penrose compactification for Minkowski space. What I have here is the following. So the boundaries of my asymptotically flat spacetimes are not going to be time like you have like in ADS, but rather null. So I have on this diagram, I basically rescaled changed my coordinates and then rescaled the metric so that everything's in this finite patch. And light rays will move at a 45, whereas massive particles will move time-like, along this arrow. So every point should be an S2, except I've shown to the north and south poles of it, so that if I drew, for instance, a trajectory of a massless particle going through, it would come in from one point on past null infinity, which is the scribe minus, and end up at a point on future null infinity, which is antipodally related, which is scribe plus. So these null boundaries, so there's also boundary components at spatial infinity, future time-like, and past time-like infinity. But most of the interesting physics that I'm going to be talking about today are along, oh, Lee, you have a question? Go ahead. Oh, you're muted.
I've been looking at these things for so long.
Yes.
Why don't we try to do quantum gravity on the conformally compactified?
Yes. So, okay, so let me think. I think that there's a sense in which like Ashtekar and others would have thought of like doing something intrinsically at the boundary already. And maybe that's the closer thing. So for us, we end up not like, at least a lot of my intuition is grounded in what I have from like radiative fields, like linear vector potentials and whatnot, that I think if I rescaled everything, I'd be screwed. And also like capturing massive particles, I think I'd be slightly worried about resolving time-like infinite. Like by not actually warping the metric down, I don't have to worry about certain issues that might happen at spatial infinity and at time-like infinity. So I think that might be one, not objection, but like one reason not to. But I do think that there's been active work in like the twistor string formulation or like Ashtekar on, I mean, you know a little bit better than me, I'm saying that, about just actually trying to quantize things on null infinity, say. Is that okay, or am I missing something?
Let's come back to it.
Sure. Because I am assuming like these things are rooted in a very rich story that if I start giving like, I don't want to give a history lesson, and I'm sure I can but
I'm sorry, I don't want to divert you. Let's go.
Oh, no. I know. So for now, I actually will not. So what I'm trying to emphasize at this point is that these boundaries are null, and there's going to be interesting, I guess, dynamics along the boundary that we're not going to want to miss, which is slightly different than what you might have if you had a different causal structure because you're in like lambda not equal to 0 spacetime. So I'm going to try to avoid talking about like the comparison to ADS CFT, but in that case, you'd have this time-like boundary. So in particular, I care about the fact that if I send in some massless particles, there's naturally starting with initial data on past null infinity, and then there's some final data for my outstate at future null infinity. And so I can think about how to like expand my metric or look at the data of the metric near those boundaries. And so what matters for me right now for the rest of this talk is essentially I'll be holding U fixed and taking large R in some of my expressions. So if you were just thinking about your Newtonian gravity, you already expect the metric isn't going to be flat anymore once you add some matter. So for asymptotically flat spacetimes, I'm going to be using the boundaries I mentioned before and performing a large R expansion near null infinity. I do that, I follow Vondi, Vanderburg, Metzer, and Sachs, and I pick a nice gauge. So I try to do my gauge fixing near this boundary and organize it in a radial expansion. I have fluctuations in the metric that are subleading compared to the round sphere metric, which capture radiative data. And I have other integration constants that appear, which the Einstein's equations will relate. So there's some constraint equations that say how the U evolution of, say, the bonding mass aspect or the angular momentum aspect are constrained based on matter fluxing through, or the fact that this zero modes of the radiative data. So basically, when I pick a nice gauge choice, I have some way to organize the components of my metric and have some sort of like physical interpretation of them, like within this gauge fixing. And I can then have my gauge fixing gives me this 1/r fall-offs for these different guys, and I want to see what is the set of symmetries, like diffeomorphisms I can do that act non-trivially at the boundary. So I write down, say, a class of diffeomorphisms that preserve the 1/r expansion of my metric in my gauge fixing. And when I do that, I find that there are these non-trivial guys in the sense of the following. So I can always do diffeomorphisms of my spacetime, but if I think of my future null infinity as my Cauchy slice for my outstate, then if I have something that's acting non-trivially on the data that I'm using to define the state, I need to be careful because they're basically of the non-zero canonical charge. They're transforming my outstate. So these guys that I happen to write down here, which like just as a test, like yes, they preserve the fall offs that are in this gauge, are going to be part of this asymptotic symmetry group, which is, yes, it's a diffeomorphism, it preserves the fall offs, but it doesn't fall off fast enough to act trivially on the data that I'm using to define my outstate. So these guys are going to be interesting to us. Basically, what's happening is that you have, what one could try to do is one could say, okay, in Minkowski space, I have my flat metric, I can do isometries of the metric. Once I've added matter in, especially say I start adding a point mass, or I add like other configurations, I'm going to lose isometries. But at some point, I have this enriched class of asymptotic symmetries. And that's what we're basically pointing out. So in this vector field, the y's have an arbitrary dependence on z. The f's have an arbitrary dependence on z and z bar. So this is much larger than Poincare. So we can give them names. We see that if we consider our symmetries to be this asymptotic symmetry group, so it acts non-trivially at the data that I'm using to define my outstate, similarly with the in-state, I can't reduce myself to Poincare, and I end up with the symmetry enhancement of Poincare. So for the super translations, essentially for each direction on the night sky, or I guess night sky you're looking at the past null infinity, you can translate the generators of null infinity. So you can do it independent U translation for each point z and z bar. And similarly, I can do local conformal transformations, which are promoting my global Lorentz transformations to ones where if I pick different patches of the night sky, I can basically boost and rotate them independently. So what's going to be fun about this is that the aerodynamics of gravity are basically governed by the spontaneous breaking of these asymptotic symmetries, because only like some subset, like the Poincare group that you used to, will actually preserve, say, the vacuum configuration if you said I'm in Minkowski space. But now you have a whole class of vacua labeled by the super translated versions of these guys. Okay, so there are now two IR modes to be wary of. And in some sense, this is like there's a nice connection between maybe what you might take for granted as something you'd want to remove from your theory versus adding them back in. So we have on the one hand, the fact that I said that we have these symmetries. We have these Goldstone modes. I can do a super translation of my vacuum. And like that's a gauge transformation in some sense. But what's fun about it, and kind of the reason why I can't eliminate it, is that if I look at, say, early U versus late U, they will differ by basically a vacuum to vacuum transition in some sense. So along null infinity, when you have anything passing through, so you have a gravitational, say, inspiraling binary system, and it's losing energy and it's losing angular momentum, and it's spewing off these gravitational waves, you're going to see when those waves hit your detector, there's some amount of energy flux. And that energy flux is going to induce a shift of the metric in the same way as you would just have if you had done a symmetry transformation. So what happens is basically is you have the same f of z and z bar, but now that's the difference between the early and late guys. So you have this dynamical shift, which is another zero mode in some sense, because it's literally like a step function. It's a very low energy change. And its symplectic partner is the Goldstone mode, which is the symmetry mode. So what I want to point out from this is not only do you have then this interesting phase space where they're symplectically paired, and you can't really remove the symmetry without removing the memory, which is something you can go out and observe. Memory effects also become a way for you to experimentally test your proposed asymptotic symmetry group. So you could play the devil's advocate, or I guess it's not the devil's advocate, so the one where you say like, I guess being a Debbie Downer or something like that. You'd be like, oh, well, you're not really in asymptotically flat spacetimes. We know there's a cosmological constant. Why are you doing this? Okay, well, if I say in this region of spacetime, which includes me as my like LIGO detector or Lisa, and this inspiraling binary system, for some approximation of that, I would like to think that I can do physics as if it were like lambda equals 0. So I can go out and I can say, well, can I see this or somehow infer this memory mode? If yes, then I would say that the asymptotic symmetry associated to its symplectic partner is a physical asymptotic symmetry that you want to deal with for that description. So and the thing is this becomes relevant when it comes to other proposals. So the leading super translations and their memory effect was something studied a while back, but I'm going to present for the rest of this talk, focus on an example which is a bit newer, and it's going to be important. So on the one hand, I propose that there is this way to experimentally test your asymptotic symmetry group proposal. But I also want to say that you can go out and see, does my quantum S matrix actually obey the symmetry? And the way that one would do that would be to translate all of these questions into momentum space. So I hand you an S matrix and I say, go and tell me, is a ward identity for the symmetry obeyed? It turns out, and this was a wonderful insight by Strominger, that you can show that the ward identity being obeyed is the same thing as a soft theorem in quantum field theory. And those were known independently. So what happens now is you have this triangle of relations. You have these asymptotic symmetries you want to study. You have their symplectic partners, which are memories you can go out and measure. And you have the way to show that there's a symmetry via the S matrix and certain low energy behavior, which is the soft theorem. And this pattern of connections is very universal. So as much as when I've been vague, I've also been appreciating the fact that you could tell me, do I care about super translations? Do I care about super rotations? Do I care about large U1 gauge transformations, etc.? I can basically repeat this story for each of the different cases. And so the paradigm here, right, is that you have some sort of fall-offs for your fields. You see what transformations, whether it's a gauge transformation or a diffeomorphism, you might want to allow. And if that is a symmetry, there should be a soft theorem telling you that it's obeyed by the S matrix. And there should be a conjugate memory mode that can go out and measure and test if it's relevant. So that paradigm is interesting. And the point is that it's a template to look for new physics. So now I'm going to focus on an example where each of the iterations were very much like new in the sense that the work of Bonnie Vander, Metzer, and Sachs is from the 60s. Weinberg was studying leading soft theorems also in the 60s. There's a lot of old physics that was recently connected, which is lovely. But then you can use this framework to find new things. So let's see. First thing to point out is the soft theorem. And this was something that Freddie at PI and Andy noticed, which is that the subletting soft theorem that Weinberg had found for gravity, if I add an extra very low energy graviton, actually extends to subleading order. So you not only have, say Q's here, scale like energy omega, I not only have a Weinberg pole for the leading guy, I also have an order 1 piece, which is universal. So the statement of the soft theorem is just that if I have my amplitude and I have an extra very low energy graviton, so that will change my outstate by adding an extra graviton. This guy is going to be proportional to, where proportional means like some linear operator here acting on an amplitude without this extra guy. So that's a relation that you're just going from perturbative quantum gravity and proving in your S matrix. So you can do that by these Feynman diagrammatics that I'm showing here and show that indeed the soft theorem holds. So on its own, that's neat. There's an extra soft theorem, and that's what Freddie and Andy pointed out. Now, once you have that soft theorem, you can follow the triangle and show that there should be a ward identity for an asymptotic symmetry. So I wrote down the super rotation vector field, and I can go out and compute its canonical charge. And if I write its charge instead of as being a 2-sphere value, so normally it's codimension 2, it would be defined at spatial infinity, I can write it as a flux along future null infinity. And when I do that, it splits into 2 parts. One part is linear in the gravitational field, and the other part is basically quadratic in the gravitational field and then proportional to matter stress tensor terms. And if I do that splitting, if I insert this guy into an S matrix element, I can evaluate the first guy via the soft theorem that I mentioned before. And you can see this as follows. The gravitational metric mode is going to be linear again in like the A's and A daggers for inserting a graviton. And you can just work out that because you've taken the large R limit, there's essentially a saddle point approximation that says that if I send radiation out to some direction, that plane wave will basically localize to a point in the celestial sphere corresponding to the direction that that observer is in compared to me. So you have this saddle point approximation, the large R limit gives you that. And then the AU integral that appears here, because I've taken my codimension 2 charge and integrated it, the U derivative along null infinity, gives me exactly the frequency dependence that I'm trying to extract. It gives me the order 1 part and projects out the Weinberg pole. And so I know how to evaluate this guy in S matrix elements using Freddie's and Andy's soft theorem. And then the fact that the ward identity holds is exactly a soft theorem. So I use the same thing happening at null infinity, future and past null infinity to get my two charges here, and I can show that there's a ward identity. So with Dan Capet's, Slava Lysov, and Andy, we use Freddy's soft theorem to show that this proposal for super rotations, which Barnett and others in Brussels were exploring, is actually physically relevant to the S matrix, which is cool. Good. So now let's take a step back and think about what this guy means for us. Okay, so we have now the Spherosaurus Symmetry. And what does that basically let us do? So I can, instead of just doing my global Lorentz transformations, I can try to now have an arbitrary function y of z. So z being one of my stereographic coordinates on this celestial sphere. Now, there is actually a phenomenological realization of this type of symmetry, which you would see in jet physics via reparameterization invariance in soft collinear effective theory. So there, if I have a bunch of different jet directions, I would be able to, in my effective field theory, to describe this jet physics, have some sort of freedom in order to basically independently boost these different jet directions. And if I wanted to play games with my y of z, I could go ahead and say, well, for any finite number of points, I'm going to construct a meromorphic function that matches the Lorentz transformations that I want to impose for each of those finite number of jet directions. So there's an intimate connection between this type of symmetry that you're kind of, I guess, seeing by the subleading soft theorem and something that you might care about if you're doing jet physics at a collider experiment. But you can also, so this is like at the scale of collider physics, but if I wanted to jump to astrophysical stuff, now I want to think, okay, what happens when I basically send some angular momentum flux into different directions in the night sky, and I can go ahead and I can measure. So if we want to test not just the, I guess, particle physics relevance of this effect, but instead astrophysical one, I would try to go out and I would try to measure spin memory. So what is spin memory? I have some inspiraling binary system, and if it radiates angular momentum, that angular momentum flux will pass through my detector, and I want my detector to basically be like a sag neck and a ferrometer. And so the angular momentum flux through it, depending on the way you set up your detector, will basically cause a phase shift in some counter-rotating light beams going around. And if you wait a long time and you measure that overall phase shift, you've essentially done this accumulated measurement of time integral of angular momentum flux. So with Sasha and Andy, we found the observable that corresponds to this super rotation symmetry. So we have now the full, all three vertices of this IR triangle, and all three of them were basically 2014 on, which is kind of neat. So like, this is like the power of this symmetry paradigm. So that's lovely. Good. Also, if there's any questions, as I go really fast and I'm excited about this, and I'm also like, yeah, I'm happy taking.
Yeah, I have a question, Sabrina.
Yes.
So
yes.
in the context of GR, there's
yes.
still not a unique definition of angular momentum at infinity.
Yes.
There isn't one. So
yes.
how would you go about setting this experiment in place? If we cannot even define angular momentum, how would you go and take even the next
So what this thing is basically looking at other patches of the night. So you're using, so I imagine that the experiment is happening in some direction of the night sky compared to where my detector is. And I would want to basically have little rockets on my detectors to keep the interferometer ring, or I guess a triangle in this diagram, aligned with reference points on the night sky. And then if I do that, then I'm basically forcing, like when the angular momentum flux is coming through, to have this this phase shift, because like I'm like not letting myself freely rotate. Otherwise, you could have a gyroscope type thing and see yourself rotate. Like, I mean, so I need to basically be able to detect the amount of angular momentum flux and rotation that would be caused by one source as compared to other places. So I don't think I run into an issue about like global angular momentum being defined. I really can, like, as long as there's some way to align my detectors, which like Bondi has a Bondi coordinate system, that's not necessarily ideal, but in practice, this is like looking at where like other reference points to make sure that your detector is kind of like not moving with respect to them.
Well, maybe we can talk later, but yeah, even if you choose Bondi coordinates, you have a problem defining angular momentum uniquely.
No, sure, but I don't have a problem, say, defining like if I have a ring, if I say my detector a certain way and I use the other points in the night sky to align them and keep that ring, I have no problem sending light beams one way around versus the other way around and measuring a phase shift.
Okay.
Right. So like there are like you can measure like the amount or in some sense too. So say I have a satellite and it's sitting somewhere, it can tell if it's rotated compared to something else. Like that's what I need for this. I don't necessarily.
All right. Thank you.
Yeah.
So can I ask a question,
Yes.
taking advantage of the fact that Louise is also asking a question? So could you be a little bit more explicit about what is an application of the symmetry and what is an interpretation of results that you need full GR to compute? So let me just explain what I mean. So when people observe this signal at LIGO, for example, right, like Louise would compute, right, computing these forms and seeing these nice patterns and so on, is it fair to say that then you interpret some shift there as some kind of memory effect? But of course, to compute it, you would need the full computation of GR. Or are you saying that this symmetry is more than an interpretation and it's a way of explaining or predicting without doing all these complicated simulations? Can you separate a little bit more what's an interpretation and what is a power, an effect of having a more powerful symmetry that you can use?
Okay, so I would, so the reason why I want to be, like, I have always taken the approach that if I went out and could see the effect, then that's emphasizing that I need to keep its canonical conjugate, which is the gauge transformation. So for me, it's easier to motivate the fact that the fact that, so here's a bit of a thing. If I said I can completely kill super translation degrees of freedom, then I would also be able to completely kill the memory effect, right? So the fact that the memory effect would be allowed to be non-zero is basically a change in some of the boundary conditions that I'm imposing, not just in literally the 1/r fall-offs, but in the U fall-offs of these modes. So if to me, it seems natural to think that if I know that radiative sources should generically induce vacuum to vacuum transitions, like that's something that I would expect to see just kind of from like basically arbitrary matter sources should source it. It would be very strange to me if it was something that would restore it back down to zero. So I think that you can see that without complicated GR simulations, just from literally looking at constraint equations along future null infinity. So, so the thing about it though is that I think that, right, like the one issue, like the problem that you have for say at LIGO is like, say you're on the ground and you have your detectors and eventually there's restoring forces. So it's not really like just some free point masses sitting somewhere that can move apart and stay apart. So there's tricks that have to go into someone at LIGO going back and like measuring the memory effect. But if I just look at, say, how my equations basically become simple at null infinity, because basically like it's like you're pushing Gauss's law up to future null infinity. You would expect the memory effects to be non-zero. I don't think I'm definitely not trying to evade the question, but like argue with me if you want me to push this further. Like what I mean to say is, as a theorist, you could even try to like allow more boundary conditions. So like I'm more worried about the question of like, can I keep going further and add U growth terms and stuff like that? Like just keep pushing it and then won't be able to see it at a detector. And like the detector is telling me, don't do that. So what I mean to say is you have a little bit of freedom in like letting yourself do too much from the theory side sometimes. But I do think that it would be rather unphysical to try to say that like the integral of the stress tensor along null infinity has to be zero. Like that's essentially what you're doing if you were going to say it's, yeah, like the memory effect would be vanishing.
No, all I'm saying is that you are describing some physical results, right? The detector at LIGO, there is a precise shape. That's a physical result.
Yes.
These jets, where are the jets, and where is the biggest density of the jets, and so on? It's another physical result.
Yeah.
And then there is a question between interpreting those results and asking where is there more energy or less energy, and so on, and deriving those results and understanding in a different way the origin of those results.
Yes.
I'm asking if you can shed light over the second or if it's mostly about the first.
I'm saying, so no, what I'm saying is like you shed light on it by saying, like trying to imagine a world where the U integral of TUU is zero. Like that's a strange world. So I would say as a theorist is looking at like the asymptotic symmetries, the fact that it would seem very, very strange to try to impose extra conditions that restrict some U integrals of matter along like your detector's world line is what tells you then that you need to include these asymptotic symmetries and need to include the memory effects. So I think that like, but you see how it's still, there's still the part there which is saying like, why can I not force this U integral of TUZ or TUU to vanish? And I think that's slightly informed by the fact that we have some intuition for the way that radiation works in the real world. Like, so like I'm trying to be a little bit agnostic on saying that it's the theorists could get it alone. But like, I mean, like every time you impose finite energy constraints or something like that on your system, when you're trying to look at the set of things you're allowing or the set of radiation you're allowing, those are informed by experiment. But definitely because it would seem so exotic to try to enforce those things, you are seeing these low energy modes, these memory effects, and predicting them for someone who actually does an experiment, if that makes sense.
But that prediction will depend on the size of that prediction will depend intrinsically on the characteristics of your source. So you couldn't say anything. So asymptotically at base, you can say, well, there will be a contribution of this sort. No. But the size of that contribution will require the full. That was what Pedro was asking.
Oh no, no, exactly. But the size of the contribution, that's fine. That's no, like that's. I mean, like I'm not worried about the size of the contribution. I'm worried about the phase space being not trivial or not. Like the contribution will be non-zero typically, and then the size is going to be proportional to whatever complicated thing you're modeling as far as like how much radiation is going to come out. I think, I mean, maybe I'm just not worried about the scales of things, but as far as like zero or not zero is a big difference, right?
Sure.
Yeah, sorry. Like, does it make everyone happy? Or no. Cool. Okay, that's good. Yes. Okay, I am happy to. Okay, so then that was Act 1, which is essentially trying to promote the idea that there's this rich symmetry structure. And what I want to do now is have a brief intermission before I go into defining celestial holography proper as follows. So right now I went through this example of the fact that I have this framework for identifying symmetries via soft theorems, showing that they're obeyed by the S matrix, showing how I would go out and experimentally test those things. And I can go with that example of super rotations directly into my celestial holography. But even if you just stop it for a brief moment at that point, you're going to see that this rich structure of infrared physics and the symmetries you get is already quite powerful. So I want to give a little bit of a teaser of things that you could do just from this point before you go into celestial holography, which other authors have looked into. The first one is when you're proving these word identities, you're essentially using the Weinberg pole. So you're using something which is like for just a single emission, this is fine, it's a 1/omega pole. If I try to worry about what happens when I exponentiate those guys, you would normally get these zeros in your scattering amplitude. And the fun thing about this framework is that it reinterprets some of those issues in terms of charge non-conservation. So I can either follow Chung and Fediev and Kulish and dress my states to have this cloud of soft gravitons around any energetic particle. Or I can think about the fact that if I don't prepare a dress state, that eventually the emission will require there to be some radiation to be consistent with essentially Gauss's law at future null infinity. So it's nice that basically there's a way to understand the fact that you might be computing inclusive cross-section summing over soft states, because eventually one of those elements in the sum is going to include the right dressing, essentially like a version of the dressing to make that charge conservation hold. And then a second, so I want to cite like Kapitz, Perry, Reichler, and Strominger for giving some insight there. And a second interesting thing you can do with it is say I found from my S matrix that these symmetries hold. I word identities for these symmetries. Now, if I add black holes into the mix, it's not necessarily guaranteed that I can like show the same thing with the same techniques, for starting from just the normal perturbative S matrix. But if I instead say that I'm going to force the symmetries to hold, you can actually show that they constrain black hole evaporation and provide a source of soft hair for the black hole. So this was work by Hawking, Perry, and Strominger. And the reason why I want to point that out is, first of all, those research lines on their own are quite interesting, and like the issue of area divergences and dressing is something that's been thought about for a while. And the black hole evaporation story is also very interesting, and it's fun that there's a chance for this to inform it. And you can actually combine the two ideas. And I just want to point out, like with Herman, we were looking at how to use the stressings and how the software degrees of freedom of the black hole can affect the experience of an infalling observer using Benny's work, but reinterpreting in terms of the HPS paradigm. So I just want to point out that we're at a stage where you have these symmetries and you can try to just push with those asymptotic symmetries and see what you can get. And there's interesting stuff there. And you can still keep building on these ideas because they're definitely still active. So that's what I'm pointing out here. So even if you didn't want to go into celestial holography, we've already learned something fun. But I want to convince you that you do want to go into celestial holography. So that's Act 2. Any questions more at this point, or I can go into my lead? Yes.
Quick question. If I wanted to be in a compact, spatially compact space-time,
yes.
So I'm concerned with, rather than the asymptotic structure, I have a topological, non-trivial maps. Is that what will happen? That the soft theorems will map on, or the soft modes will map on to topologically non-trivial modes on S3? So that exciting a soft mode is like,
yeah, I'm just not sure how you would excite it, if that makes sense. Like, I would be worried if I would, like the question I would have is whether I agree that there is a sense in which the low energy structure should include like topological terms, but I would be worried about the ability to go from nothing to that term, if that makes sense. Like I don't know how to imagine doing a transition, like a vacuum transition of that sort. I mean, I guess like I would be worried, but I'm not saying that you can't. I think eventually we want to, like, there's been recent interesting work by Andy and collaborators on like going to 2-2 signature and whether or not you have a celestial torus and things like that. And definitely we'd want to look at modular invariance there. If anything, I would advocate that what we're trying to set up now is doing everything locally so that once you have a good reason to do different topologies, you just like build up from there.
good. Okay.
But maybe if you could patch things up, then you could try to have a story like that. If there are degrees of freedom that their global like matching is what gives you the non-trivial topology, there's something there.
Sorry, can I ask something?
Yes.
You said, did I understand correctly that you just said right now that if it was a torus, we should impose modular invariance?
I think I would try to see if I could. And I'm not saying, no, I'm not saying, how do I want to say this? Right now, the issue with the 2-2 story and the torus, I think that the moduli parameters are fixed. Like for my, this is a recent paper, so I need to absorb it more, but like this torus they're talking about is the one you get from just taking Klein space and the conformal compactification. But how do I want to say this? It's not, I don't want to say that I know what to do with it, but I want to say that I would try in earnest to match as much CFT structure as I could and then see what happens. Because like for us right now, we don't have as quite a clear interpretation, I guess, of like what I do to this 2 manifold, which is basically like sitting at the light cone, the edge of the light cone. And I guess propagating that into the bulk and what the geometries are. So it's a little bit harder to motivate whether or not you would sum over different like modular parameters from the amount of the duality that's been constructed so far. But what I would try to argue is that we definitely know how to like take operators close to one another and things like that. So if we then had a conformal block decomposition or something like that, we could try to play around with how you build up that local consistent celestial CFT into something that could like take into account different non-trivial topologies for the CFT. But I am not making any claim about whether it should be like we're not there yet. Okay, is that fine?
Yeah.
Okay. I love that I'm getting called out and like, oh, we could do this. No, you don't know. Okay, good. So Act 2, new framework for scattering. See, there's a lot of fun stuff that's to be there, I think. Okay, so right now I have spent a bit of time on setting up this IR triangle. And what I wanted to do, at least the example that I focused on, is directly related to the next step, which is this 2D celestial CFT. So my claim right now for the next part of the talk is going to be that 4D S matrix elements can be mapped to 2D correlators on a 2D celestial CFT, and that mapping is useful and not just kinematics. Okay, so this is a little bit of a review of some things that I said maybe too quickly before. Of course, you have your global conformal symmetry is just Lorentz invariance, right? So if I take a point in the night sky and I boost towards it, I'm going to see this like warping dilation effect towards that point. And that's just global Lorentz invariance. Now, I also mentioned that we have this Spherosaurus symmetry. And so we actually have a 2D stress tensor, which gives us like the local conformal transformation. So you can find some value of this memory effect mode. So classically, this guy is the memory effect for spin memory. Quantum mechanically, it's this low energy gravitational operator, which is a candidate stress tensor. And insertions look a bit like your standard 2D conformal field theory word identity for a stress tensor insertion. So you can basically massage the subleading soft theorem to look like it's a stress tensor near some other operators. So that's cool. So when I pointed out this IR triangle and I had soft theorems being related to word identities for asymptotic symmetries, that's really not the only equivalence that's important here. You have the one side where you have, with like Slava say, that the asymptotic symmetry is physical using the soft theorem, but then you also have that you can naturally rearrange these word identities in terms of 2D currents. So in this case, it's a stress tensor, but there's also like actual like it's Moody currents, say, for the gauge theory analog. So we want to go to 2D. What we have at this point so far is essentially these memory mode operators, soft operators, are currents in the 2D CFT, but we can extend the map over. So in that one, I guess, equation right here, where he says, oh, look, it looks like T's and O's, we were a little bit quick. These H's right now are not actually diagonalized. So what they care about is basically boost eigenstates or Rindler energy eigenstates, that eigenvalue rather than the energy. So one really needs to take advantage of this super rotation symmetry and to have this manifest like stress tensor that you can then like use in your 2D CFT. You want to change your scattering basis states. So that's what Shuhung, I, and Andy were set out to do. What you want to do is you want to go from translation eigenstates to boost eigenstates. And in hindsight, that's not actually that big of a deal because you just take your on-shell space of momenta. So you have a light cone of on-shell momentum for the massless case, or you have a hyperboloid for the massive case. And you can do the appropriate convolution to make that guy transform. Like instead of a plane wave, it transforms like covariantly with definite weight and spin. So for the massless guys, it's particularly simple. It's just a Mellin transform over energies. For the massive guys, depending on the spin, it's a different Green's function, but this is just using your bulk to boundary propagator, where now you still have this interpretation of the CFT being the boundary of this hyperboloid, but this Euclidean ADS or hyperboloid is your on-shell momentum space. So there's lots of just, because this is like, because ADS CFT is so active, we have a lot of nice equations for integrals of these guys ready to go. And you can show that you can construct a basis in this manner. So first thing to note is the Mellin transform itself doesn't actually take you to the wave function that transforms covariantly with definite weight like you would want here for the metric, say. But what it does give you is it gives you something gauge equivalent to that. And that's mostly what you need for just going and taking an amplitude and that's massless and constructing your correlator. And you can show with integral relations for these Green's functions, or basically also just, I guess in the Mellin case is simpler, that you can form a basis of all your single particle scattering states with the principal series spectrum. So that's great. So we know that whenever we're talking about scattering in our normal S matrix, we prepare our momentum eigenstates. We can go to instead to boost eigenstates, and we know what spectrum we would need to capture all of these radiative states. So yay, team. So one thing I want to point out to I guess make the dictionary a little bit more palatable is that there is a sense in which for massless guys, you can kind of view it as an extrapolate dictionary. Obviously, this is a codimension 2 guy, so it's sitting at a cross section of null infinity. But instead of doing my normal LSD formalism and picking out poles of my correlation functions, I can use the saddle point approximation and basically pick out the creation and annihilation operators on the in states, sorry, there should be daggers here, and out states respectively, by essentially going to large R and integrating my metric along null infinity or along past null, future or past null infinity. And these light ray operators will be constructing the definite plane wave in and out guys. And then I Mellin transform that out to give me basically a delta dependence instead of a U or omega dependence. So you can think of this S matrix element already as a bunch of correlators of these operators integrated along null infinity. And now they're sitting on the celestial sphere because we've created out that light ray direction for a dimension. that's continuous. So we still have like that degree frame. Good. So now I'm at the stage where if you tell me that you have an amplitude, I can tell you how to get your celestial CFT correlator or celestial amplitude, whatever you want to call it. Take your amplitude, do an integral transform, got my answer. Now, what's interesting about that map right now is that it's going to probe scattering at all energy scales. So for this Mellon transform here, I'm trading omega for delta, but I'm integrating over all energies. So you might be worried like, okay, I have my tree level amplitude or I have an amplitude in an effective theory. What gives? Like, I really need to either be confident that I have the amplitude to all energy scales or be fine looking at some like part of that full amplitude. So that's looks like a bad thing maybe, but it's actually where you possibly have the power for that. And then another thing with this map is because obviously this map was inspired by superrotation, and it makes these the currents like actually like currents in a CFT. Like we're putting the IR symmetries front and center in this picture by going to this 2D CFT. And so we think that we have a new vantage point now to examine interesting features of this original amplitude by doing this transform. So that's going to get me to the third part of this talk, prospects of this framework. Good, I think I'm fine on time. Okay, so now I had a very, what's it called, like where you advertise. my abstract was trying to like get you here because I want your help with this stuff. So let's explore what celestial holography can do for you and what you can do for celestial holography. So I teased with 3 questions that we might be interested in. Like ultimately, I guess, depending like what subfield you're working on, at some point, some of these questions are like come up in your research. We want to know what symmetries are of nature. We want to understand fun stuff like black hole physics, how they process fun information. And we want to know what's happening in ultraviolet, but what's happening beyond our reach. Can we use theory to push that? And for me, I'm also going to, I guess, phrase that in terms of like, what's a consistent scattering amplitude? Okay. So I'd like to say that I've at least hinted at how the first 2 of those points are touched on, or at least like the inspiration is somewhat realized in the sense that when it comes to looking for symmetries, we have this framework, the IR triangle, to go and find new symmetries or like different aspects of it that might be missing. And basically every time we have a soft theorem, we try to find a symmetry interpretation of that, etc. So like, there is a way to basically pump through different examples because there's 3 things that are related, and in different cases, some of the 3 are known or not. Like you can go and you can try to find new symmetries. And the second point, we've talked about how those symmetries can constrain black hole evaporation. So at least there's some contact with that interesting set of questions. And then for the rest of this talk, I want to pose some questions about how one might try to use the framework of the celestial amplitudes to say something about what a consistent celestial amplitude has to obey. And that might tell us something about, say, the behavior of scattering or other questions that might not be easily addressed from the point of view of, I guess, just like momentum space. Good. Okay, so now I want to phrase basically the approaches that one can take into 2 sets. So like along the line of like proceeding with celestial holography, the main theme is to try to complete the dictionary. So we already have what these local operators, so our scattering states are mapped to, say, these local operators with different conformal dimensions on the celestial CFT. But even though we kind of have this dictionary between any of our external S matrix states and our operators in the celestial CFT, there's a lot of the dictionary that we don't know yet. We basically want to see how features of a standard conformal field theory are encoded in amplitudes, whether that's like operator product expansions, conformal block decompositions, etc. How amplitudes features are encoded in celestial CFT. How do you see locality and unitarity in 4D bulk like emerging or in the celestial CFT? And then like a legit classification program. So the currents that we have are a stress tensor, but every time you have gravity, you not only have a stress tensor, you also have the super translation generators. So the symmetry structure is going to be very different, and you can try to perform an algebraic classification type program to these celestial CFTs, and hopefully, because there are so many symmetries and they're put front and center, there's a chance that hopefully that'll say something about the S matrix once you Mellon transform back. So the second parallel approach, which is also a bit overlapping, especially for the first 2, is to really just try to connect our story to other subfields, because that's where you can reap like the fastest rewards, in the sense that if I know what I'm doing is the same as what someone else is doing but in a slightly different language, then I can take all of these results about like how interaction terms are like constrained by causality, etc., and translate it to my framework, and then say, oh, look what we've learned in this framework. So for instance, some that come to mind are the amplitudes program, and including like NEMA's EFT Hedron, Bootstrap for the Celestial CFT, which is going to be a bit different because it's a quite exotic Celestial CFT. There's like, it seems like you should be able to connect to twistors, and then also edge modes, which either you might not say this is loop quantum gravity, but at least it's like canonical gravity. I think that there's some fun things there that we'd love to connect. Okay, so what I want to point off is that these celestial CFTs are quite exotic. So in the first set of papers where we're just doing this map, it's easy to get caught up in what isn't what you want it to be for a celestial CFT. So first of all, you have these conformal dimensions, which are complex to give you this basis for your plane wave scattering. And translation invariance isn't manifest from the point of view of these, like basically Lorentz boost eigenstates. So they give you these strange singularities in the cross ratios if you have massless scattering. And so one could be slightly worried, these features like, this doesn't look like my yellow book CFT. But the ideology that works in this case is you want to say, we have some exotic CFT. What is it like, let's go and be willing to rederive things that we take for granted about normal 2D CFTs and see what we get. And what I want to emphasize here is that it's also useful to not try to just transform any particular amplitude. So we started with some MHV amplitudes, and then a group at Brown was like doing like NMHV amplitudes and KMHV amplitudes. So instead of restricting yourselves to take an amplitude, transform it, you can try to instead transform generic features of amplitude. And that's the direction it's going, and that's where the progress is coming nowadays. So I want to point out that ideology and try to, I guess, advertise, like have people try to do that. Okay, so celestial amplitudes are described by, for each of these operators, there's points in the celestial sphere and a complex conformal dimension where the scattering states can be mapped to just the principal series, but you can analytically continue off of that in the complex dimension plane. So you can ask maybe what happens at special values of the ZI and what happens at special values of the delta. So just to read off some early interesting results by a bunch of people, so I put at the bottom, is that so celestial OPEs organize collinear limits and scattering, and different values of delta basically resolve different soft theorems. So normally you'd have to look at different orders of something order in omega near the origin in momentum space, but instead they become poles at different values of delta. Then whether or not the Mellon transform is even well defined depends on how the amplitude scales with energy. So essentially in this picture I was drawing before here, I'm taking my momentum conserving delta function and transforming it along with the amplitude. And when you're doing that, you're basically saying, I have this modulus for each of the momentum, like the energies. You give me some directions, and I want that polygon to close. But if it does close, then I can dilate the whole thing. So I basically am probing the overall scale of the how the amplitude scales with energies. And so for amplitudes which are conformally covariant, things are nice, especially for your gauge theory. It's exactly enough to give you a delta function. But because you're probing things at all energy scales, first of all, you have to worry about what other particles are coming in or what's happening at higher energy scales than your effective field theory is valid for. It turns out that when you include stringy physics, you include the tower of states that you would get. Steber and Taylor noticed that damping that you have, that soft behavior in the UV, makes the Mellon transform well defined. So there's this teaser, this interplay between how you might like a theory to behave in the ultraviolet and how this amplitude is going to be like an okay thing to work with, like the Mellon integral converges. So if you took the point of view other than hoping that the Mellon integral should converge, saying yes it has to, then you're already seeing that something must happen in the UV. That's cool. So I think that attitude is what I'm trying to convey, and also is the reason why this thing could be useful. So the list goes on for interesting things you can do. I've just listed a couple of things here that I've been personally engaged with a bit. Some questions of asymptotic symmetry groups can be addressed from the point of view of the conformal basis, where you identify diff S2 versus Spherosaurus generators as coming from different boundary conditions associated with different delta guys. Double copy relations persist. The classical version of those, you can see that you have exact solutions to GR, so you can think about scattering on different backgrounds. and null state relations constraints, celestial CFT correlators. So there's a lot of technical details which are fun to work out because you get intimately familiar with the celestial CFT and what's a little bit different than normal CFTs and stuff. So there's also a lot of open questions, which is one I want to leave you on, which is some questions that were raised by people at the workshop from last week. Is what do factorization channels look like for celestial amplitude? So Nima was pointing out that maybe you don't want to worry about like transforming the full amplitude, but look at what happens at special values in the same way that you're trying to map features of what you're used to in like scattering amplitudes and to this celestial story. So you can try to break up the question into like, oh, I get some funny singularities when I'm looking at low point scattering amplitudes, but if I'm looking at that as part of a larger amplitude, I might be able to say something there. Should we be going to 2-2? There's some fun stuff about a celestial torus that Andy and collaborators just published, which is fun to look at. Can we define a bootstrap program? And I know this is something that a lot of people raise, but I want to claim that if we do come up with it, I want to change the name to bootstrap because it's a boost eigenstate version of bootstrap, whatever that may be. And then can we make a nice connection to edge mode? So that's the slide I wanted to end you guys on. And I'm just about my 1 hour. So yay.
Thank you.
All right, thank you, Sabrina, for that very exciting talk. So for starters, are there any student questions?
Okay, Justin?
Justin, go for it. Oh. Justin, did you have a question? I see a hand,
yes.
But you're being...
Sorry, I was struggling to unmute. So one of the things I was wondering about was if you could re-explain what it means to do a Mellin transform of a correlator of massless things again, because it seems like for like a random amplitude that just doing a Mellin transform causes it to blow up. And so I was wondering if this means that amplitudes which can be Mellin transformed are somehow extra special.
So, okay, so at the level that you're looking at it, the extra specialness is like that the sums of the dimensions add up to the right value, like for these operators to make it so that it would be scale invariant. So what you can do at the practical level there is you can analytically continue the values of the dimensions so that it at the point where it does converge and basically probably gives you a delta function for the sum of the energies. But I think the interesting thing about it is more that eventually whatever corrections you have are going to come in and change that behavior. And the funny thing about it, so there's a recent paper by Nima and Anna and Monica. So hopefully next week you'll hear a little bit more about that aspect of it. Is that like you can you kind of in their point of view they have this like mass parameter and you get the non-analytic behavior by some weird like large M limit of some like field you've integrated out. So I would take it as a feature rather than a bug, but in practice, if you want to deal with not being able to transform an amplitude, you can always deform the contour for the values of delta and make it so it converges, I think.
Okay, and maybe this is related, but then I know there might, I think I saw some papers maybe by Poom and others on higher loop amplitudes, but I know that they were studying n=4, which is particularly special. So is there anything? Yeah,
I mean, so my attitude is always, I mean, I guess like, this is the thing where you think it's going to be, you take it for granted and then people will come up with interesting results like by not taking it for granted. So my approach is always, I'm transforming the external states. Sure, you can add loops to it, fine. But there is a play, I guess, between the energy scale you're integrating over and if there are any UV or IR cutoffs. So they had a nice relation where they were taking like some sort of like all loops result that was known in amplitude and converting it to the spaces. Personally, like, I mean, like I would just try to have fun with like, I guess, doing some regularization. I guess I would probably not want to do dim-reg because I want to not mess with the celestial sphere, but put a cutoff in, do the integral and see how that cutoff interplays with the values of delta. Like I think I think it's straightforward to try it for other things, but I would also look back at that paper and see if they were trying to be more general, because in principle we are transforming the external states. So you can do this transform to the amplitude and then see what happens.
Great. You. Are there any other student questions? If not, Luis, you might go first.
All right, thank you. So Sabrina, thanks for the talk, which a fraction of it went quite above my head. So let me just ask you a very simple question. So in all this business of dictionary holography, there is a lot of post-diction. So one uncovers things and relates them. Yeah. Can you point me to one prediction or one particular path that is quite insightful that one could then, armed with what you have already identified, I can go and learn?
Okay, I mean, I don't think that super rotations were known. Like, I really do think that the example I covered is the closest to a pre versus post diction, in the sense that, like, okay, so Bondi, Vandenberg, Metzer, and Sachs, they didn't want to add punctures to the celestial sphere. So they, even though they had super translations, they didn't want to allow super rotations. So I mean, there's a post diction in the sense that, like, everybody is now comfortable adding singularities to the S2 or whatever. We've been more relaxed with our boundary conditions, but like, it wasn't clear that that would even be obeyed by the S matrix. Like, the sublating soft theorem was not known. The fact that you would think that you have not only energy conservation but angular momentum conservation is what led, say, like, and also the proposals by Barnish that maybe you want to include super rotations is what led Freddie and Andy to look for that soft theorem. So, like, that wasn't known. Spin memory wasn't known. It was the fact that we knew that the electromagnetic case corresponded to physical observable, that the super translation case corresponded to physical observable, meant that we thought we could find the spin memory, and we went and we found it. Like, I consider those predictions, not post-dictions. Like,
well, yeah, I could argue against that, but back in those days, relativists were trying to get rid of things that were a nuisance for them, and they were just fixing gauge in a particular way so that those things would not be there. So, but fine, I would give you that. But let's say now that you have a much better understanding of what this dictionary is all about,
yeah,
what's the next step? What is it leading to? What is it pointing as the most exciting thing I should do next?
Okay, I mean, I think the most exciting thing to do is to a little bit more post-diction, but then eventually get enough intuition to how to make a prediction about, like, how the amplitude behaves at, like, delta goes to infinity in all directions, say. Like, basically, I want to find if the OPE naturally only gives me, like, if I do conformal block decomposition, that all of the channels correspond to only the external states I've created, or whether or not I need to have somehow operators that are like composite or something like that. Like, are the channels corresponding to just the single particle states I've created, or something more? So I can do the conformal block decomposition and look at what's in the intermediate channel and see if that means that I had everything to begin with, or if I was missing something, like, say, like, from collinear limits. Like, that might be answered in the negative depending on what Anna finds out with her 2-2 guy, but in the Euclidean conformal block decomposition, I think it's still open. I can go about and I can try to see if, for instance, if there was a way to see if there was modular invariance or something like that, if I go to, like, a different topology for the boundary, I could go and I could test. Let me see what else I can test. So I could test, so whether or not, like, how much do I want to, like, okay, so my amplitude, I assume there's analyticity, but then I assume that I can add the momentum conserving delta function. Like, am I getting rid of some of those singularities by adding, like, extra higher mass states? I think I should be able to, with better intuition for the behavior in delta, make some predictions there. Okay, one other question. Okay, so
that sounds good.
Like, naively, okay, there's like multiple expansions. Like, is there some part of these sublating soft theorems that is universal, because I am scattering something that's a composite particle with higher multiple moments, and that has a conservation law, or it doesn't? I mean, there are things you can phrase from the point of view of, like, looking at residues at different values of delta in this plane, and then see if that, like, informs you, or like how it gets killed, like how it gets killed in a different way, maybe, than an expansion in omega might not be universal. Same.
All right, thank you.
All right.
Lee, go.
Yes. So, is there a chirality to this structure? If you want to make contact with twistor theory, with Ashtikar, with Fabansky, you want to look for something like the Penrose's self-dual graviton.
Yeah. So
the whole thing, you know what I'm saying? The whole thing is analytic on one helicity side and is integrable. And the complications all come from folding in the wrong helicity.
So all of our, like, for instance, the states that we create that are definite delta, that are single helicity, it's a complex solution, but they are, like, self-dual or anti-self-dual. And some of the problems that come in actually are phrased in terms of these degeneracies of the soft theorems. I'm very interested in connecting to history, but I'm afraid I'm going to say stuff that I know rather than like try to jump into their version of it. So what we see is the following: there's some weirdness about soft limits, say of opposite helicities, whether or not like they don't commute. And what you also see is that, for instance, the positive helicity and negative helicity gravitons or photons have a degenerate soft theorem related by the shadow. So what's somehow happening is like you could try to put everything into one chirality by taking negative helicity guys, say, and shadow transforming them to positive helicity always, and work there. I think that I'm not 100% sure that makes them all self-dual versus anti-self-dual, because I think it was shadow versus non-shadow that was one or the other. But you can definitely there's a way to construct states which are like, we have these anti-self-dual states, and you can look at them as backgrounds. And I think that because the natural guys are these self-dual or anti-self-dual states, that's why I'm thinking that they would be connected. I'm not sure exactly where you're going to run into the issues of different helicities from our point of view, but you definitely do see something about like the fact that the two currents aren't independent somehow.
Okay.
That is, I think, sounds very relevant.
If you're that far with me, do these two spheres, which are your celestial two spheres, somehow get to be two singular, so there's really a cohomology of them?
So that what I was like. So the reason why I was interested in trying to make this connection, and also where like I went to ask Lionel for help, and hopefully he'll help us, like, is because exactly it goes into like more of a cohomology statement. So right now, what I want to, the thing that teased me like a little bit is that if you write everything in terms of your spin frame, okay, so when you give me a null direction, I can construct a nice natural like tetrad for it, and I can construct a spin frame for it. And the two spinners that are appearing are related by something very much like the incidence relation that you see in twistor theory. Now, obviously, like these are just two component spinners to describe, say, like my like polarization vector or tetrad or whatever. But I would think that they would come out from some sort of like pull from the Penrose transform. So I just want to write, like, I want to say like my conformal primary wave functions are a basis for scattering. Can I write that as the elementary twistor states? And I think that that's just showing what I have to go through Todd's textbook on this to show that I can or can't.
Right.
Now I'm confused about whether or not I'm only going to get integer delta, because exactly like the homogeneity of it matters. So I don't know how I'm going to get like non-integer delta.
From cohomology classes.
Yeah, or change the two. Yeah.
Beautiful.
Yeah, but I'm talking about things where I was like, I don't know that enough yet, but I want to know it. I'm like very interested.
All right. If there are no further questions, in view of time, let's thank Sabrina one more time for a great talk.